So we finished our marathon of lectures on Dedekind domains, and this somehow was telling us that rings of integers, which are Dedekind domains, have very nice ideals. We know that how they all look like. They can all be generated by two elements, for example. We know that every ideal can be factored uniquely into a product of prime ideals. And we checked. The last thing we did was check that Dedekind domain is a UFD if and only if it's a PID. So now we're going to try and continuing this theme of working with ideals as if you're working with numbers. Let's go back and remember we defined like the norm of an element. We can now try and define the norm of an ideal, and this will be quite powerful for studying the structure of ideals and actually writing these ideals down by understanding their norms. So this section is called norm of ideals, and let's start with a definition. So what is a norm of an ideal? So definition 3.4.1. So I was using a K be a number field. From now on, I'll probably go back to just working with number fields, although all of this will work for Dedekind domains, but we don't care about number fields. A K be a number field. And let's take some ideal A and OK, an ideal. Now we define the norm is just to be the size of the quotient. So we define the norm of A of this ideal to be, so it's denoted by the norm of this ideal A. I'm not going to put any I won't put any subscripts on the norm because this norm is somehow it won't really make sense for us to talk about norms over other fields, or we'll just be talking about the norm down to the rational numbers, imagine. But the norm is defined to be the size of OK mod this ideal A, which we saw before because we're in a Dedekind domain. Well, OK is a Dedekind domain. An ideal, the quotient of OK by an ideal is always a finite group. We did this in one of our Dedekind lectures. So this is the definition, and let's try to start justifying why this thing is called a norm. So you will see some properties of this. That start to justify the name norm. So here's a proposition. So this tells us that the norm behaves multiplicatively as somehow we would expect. So 3.4.2. Again, we have a number field. And we have two ideals. So again, I'm just going to be working with standard ideals most of the time. One can make this definitions work for fractional ideals. You can think about how you would do this. But we're just going to be working with ideals for now. Maybe we'll have to use it at some point later on, but for now we'll just stick with this. So we have a number field with two ideals, then the norm is multiplicative. So the norm of A times B, same thing as the norm of A times the norm of B. Great. So remember that norm, the previous norm that we had for elements was multiplicative, so this makes sense. So here's the proof. First note that because I can factor every ideal uniquely into prime ideals, it suffices to just check this when one of these A and B's is a prime ideal. So by factoring A and B into prime ideals, it suffices to prove that the norm of P times B is the same thing as the norm of P times the norm of B, where P is a prime ideal. And B is a proper ideal. if one of these ideals isn't proper, then their product is a whole ring, and then it's immediate to follow, because the quotient of this of OK by OK that says that has size 1, so there's nothing to check. Okay, so this proof somehow basically relies on group theory, and it basically relies on us remembering that ideals are just additive groups with some extra property on them. But we can somehow just do some group theory because we're just trying to measure their quotient. So I'll just say by group theory, this is like one of the third, fourth, I don't know, the nth isomorphism theorem, one of these things that we're going to be using at some point. But first thing to remember from group theory is by group theory, this group B quotient out by P B. Notice that P times B is an ideal and it's contained in B, but these are also groups, so I can take, so this is a subgroup of this, and these are all abelian groups, so I can take the quotient, doesn't worry about anything. This is a subgroup of OK mod PB, since B is a subgroup of OK, and their quotient is so this is a subgroup of this, so I could take their quotient group, and if you go back to go through, you'll remember that you'll notice that this is just OK mod B. Somehow the p's cancel out when you do the quotient. It's not exactly that, but this is just if you haven't seen it from group theory, then you're happy to we can just assume this. If you don't believe me, then try and prove it. So what does this mean? So this means that the size of OK mod P times B is the same thing as the size of OK mod B times the size of B over PB. I have my big group, and I have my subgroup, and I have their quotient. So the subgroup and the quotient, somehow the size of them multiplied, so it's the same size as the full group. So really we'll just follow from like the first isomorphism theorem for groups. So notice that this is just the norm, by definition, this is the norm of B times the size of this thing. And on this side, this is the norm of P times B, by definition. Remember, the norm was the size of the ring of integers mod the ideal. So this side is the norm that we're trying to calculate, and we have the norm of B, and then we have this factor here. So we need to show that the size of this thing is the same thing as the size of OK mod P. Great. So since P is not the whole thing, it's some non-trivial prime ideal, and say fractional ideals form a group, we have the following. So we have P times B has to be different from B, because otherwise just multiply through, we have this fractional ideals being a group, we can multiply through by P inverse, and then you get P is OK. So you'd be able to multiply through by B inverse, and then you'd get P is OK. Say otherwise, multiply through by b to the minus 1 to get P equals OK, which is not what we want. It's not in the situation that we're in. So because these two ideals aren't the same, so I'm going to pick some element which is in their difference. So I'm going to let some element B be X be some element in this ideal B, but not in the subgroup B times P, which I know exists because these two ideals aren't the same. And I'm going to consider the map. Let's consider the map from OK to B over B times P, given by you send an element A gets mapped to A times X, and then you reduce mod this ideal. So it's a times x, and then you just somehow reduce this line. This is in p, so this a times x is in the limit of b, and then I'm just composing this with the quotient map to be p. So I'm just considering the cosets. So we have this. What is in the kernel of this map? The kernel of this map so it contains this ideal p, because if a was in my ideal p, then a times x is going to be a is in p, b is in x is in p. Sorry, the other way around. A is in p, x is in b. So their product would be in bp, so then it would be 0 in this quotient. So anything in the kernel, anything in p is contained in this kernel, and the map is non-zero by my choice of x. Because we have some x that works. Therefore, the kernel is an ideal. Kernel is always an ideal. In this case, it's an ideal containing. I'm going to say proper. It's a proper ideal containing p, but p is maximal, right? So it can't be containing any proper ideal. So the whole unless it's the whole thing, the kernel is a proper ideal containing p. So since p is maximal, we must have the kernel is just this ideal p. Therefore, this map is injective. Oh, sorry, not this map. Therefore, yeah, the following map, if I quotient out by this thing, this map PB, I know that the kernel of this map is the ideal p, so I can just quotient out by this, and it doesn't really change my map. So I have this map, and this map is injective. So all we need to know to prove what we wanted to prove, that they have the same size, is now we need to show that that it's bijective. So we want to. So remains to show. Remains to prove that this map is surjective. So to do this, we just need to invoke the fact that we have unique factorization of ideals. So note that by unique factorization, we can't have any ideals strictly between B and PB. Why is this the case? Since otherwise we'd have something like P times B contained in some ideal C contained in B. But remember that containment turns into division of ideals, so which means what does it mean? So it means that B would have to divide C. This is from this containment here, and then the other containment would tell us that B has to divide BB. So by uniqueness of factorization, either B equals C, or C is the whole thing, it's BP. One of these two things has to hold. Yeah, B has to divide C in this. Therefore, because there's no ideals contained in between them, therefore, if you just consider what this, if you consider what the sum of these two ideals is, this can't be any ideal contained in between these two things. X is in the limit of B, so this has to be the full thing, so this has to be B. But this shows that the map is surjective. Great. So this is a technical proof, lots of group theory coming in and so on. But the result is that norms are multiplicative. So that's great. The main group theory, the first bit isn't so hard. The main group theory is checking that this quotient or that this thing is isomorphic to OK mod P. But we're using tricks. But what does this norm tell us about ideals? So here's a nice little result that follows from having this norm function. So it's 3.4.3. So if I have a number field, and I have two ideals, one contained in the other, so A contained in B, contained in OK, non-zero ideals. I know I said that I don't really care if these are, when I write containment, it could be equal or not. I'll just put the thing here to try and be a bit more precise. But I have non-zero ideals, then what's the statement? Then these two ideals are the same if and only if the norm of A equals the norm of B. So if we had a good way of figuring out norms, and we had a containment of ideals, and we could somehow try and tell if a sub-ideal is the full thing. But I'm just taking the norms. And we will see that we have good ways of calculating the norm. So we'll get to that in a bit. So let's prove this. So one direction is clear. Clearly, if A equals B, then they have the same norm. So there's nothing to do. So let's check the other direction. So note that for the converse, note that since we have A contained in B contained in OK, we can use a Tower law, which works for groups. So the same statement as we have, but just works for measuring the sizes of the quotients of groups. Gives us that the size of this quotient, same thing as K mod A times B to A. I'm just towering up. But just notice that clearly by definition this degree is exactly the norm of A, which by our assumption is now the norm of B because we're doing the converse, which is the same thing as OK to B. And so we have this number and this number being the same, so this thing has to be 1, so these group ideals have to be the same. So it goes on, giving the result. Cool. So couldn't quite use this Tower law thing before for proving the size of these ideals, because in the previous theorem, for proving this size, this thing here, we didn't have for these sorts of things, we didn't have containment of these ideals, so it didn't quite work. But anyway, so great. So if we have one ideal containing the other, we want to figure out if they're the same or not, then they have to have the same norm. This is a nice little lemma to have. What do we know about the norms of prime ideals? So here's the proposition 3.4.4. If I have a number field, and A and OK and ideal, if the norm of this ideal is prime, so this norm is always an integer, it's a prime number, then A is a prime ideal, And conversely, if P is a prime ideal, then the norm of P is going to be P to some power for P a prime number and F some positive integer. So if you have any ideal and you take its norm and you come out with a prime number, then that ideal will have to be prime. And if you have any prime ideal and take its norm, then it has to be a prime power. Great. So let's prove this. So let's assume it's not prime. So if A is not prime, then we can factorize it. Then write, A equals P times B with P a prime ideal. I can do this by just, I know that every ideal can be factored uniquely to prime ideals and so on. So I can factor this like this with B not being the whole thing, because I'm assuming that my ideal isn't prime. Then by the previous, not the previous, two propositions above, by the multiplicativity of norms, by proposition 3.4.2, we have the norm of A is the same thing as the norm of P times B. It's the same thing as the norm of P times the norm of B. But we're assuming that the norm of A is a prime number. So since the norm of A is assumed to be prime, this means either the norm of P equals 1 or the norm of B equals 1, which implies either P is okay. Think of the only thing that can have norm 1 is okay, or B is 1. B is the whole thing, which is a contradiction. Cool. So that's the first statement done. If A is ideal, if the norm of A is prime, then A is a prime ideal. So let's do the converse. So let P be a prime ideal. So it's a prime ideal, therefore it has to be maximal. It'll be a prime ideal, therefore maximal. So the quotient, OK mod P, is a field. In this case, technically it's a finite field, because we know that the quotient is always a finite integral domain. Well, it's always finite. We know that P is a prime ideal and maximal, so this is a finite integral domain, so it's actually a field. This is some finite field. And we know that all finite fields, the size of them is always a prime power. This is one of the statements I gave you ages ago. So this is it's a finite field, so its size is a prime power. Which gives a result. So this one was pretty easy to prove. But yeah, the norm can somehow tell you about if your ideals are prime or not. And here's maybe the best reason why this deserves to be called the norm. So here's proposition 3.4.5, which is that it somehow extends the previous definition that we had. So if I have a number field and I'm going to let alpha be some element in the ring of integers which isn't 0, so some non-zero element, and I let alpha denote the ideal it generates, then what do we have? We have the norm from K to Q. The norm of this element is the same thing as the norm of, well, the size of this thing, which is the same thing as, well, the norm of this ideal by definition. So the norm of an ideal generated by a single element is the same thing as the norm of that element. So this is maybe the best reason why this should be called norm. So let's prove this. Let me start with an integral basis of OK. So let E1 to En be an integral basis for OK. Then if you think about this, then if you multiply them all by alpha, you get, this is an integral basis for this additive group generated by this ideal. So it's an integral basis for this thing. Every element in this ideal is some multiple of alpha. So if I have an integral basis of OK, every element can be written in terms of this. So if I want it to be in alpha, I need to make sure that every element is divisible by alpha. So clearly, this will give me my my basis. On the other hand, and since we have alpha is some ideal contained in OK, which as additive groups is isomorphic to z to the n. Here, I should clarify, n is the degree of my field. So we can make sure we can choose what is it? The EI. So we can ensure our integral basis is such that we can choose the EI such that there exists some mi in z with m1 e1 mn en an integral basis for this ideal. So I'm going to write down, I'm writing down two different bases for this ideal generated by alpha. And because my ideal generated by alpha lives in some time like z to the n, I can always somehow multiply through by some appropriate mi's to make sure that my original basis is just looks like some copies of z to the n for my ideal alpha. So alternatively, this follows from like the structure theorem for finitely generated abelian groups or something. But don't worry about too much. But I'm saying that I have two bases for my ideal alpha. One which is obviously like this, and one because of everything just looks like some bunch of copies of z to the n as additive abelian groups. Then I can make sure that this works. So if you think of what this means, then this thing in terms of this basis, I just said that the top thing looks like a bunch of copies of z to the n. I'm doing this all as groups. So this is just isomorphic to z mod m1 z cross z mod mn z. Each of these m's somehow quotients out one of the copies of this thing. So as a finitely generated abelian group, this is what it looked like. All finitely generated abelian groups look like this. And therefore, what's the size of this thing? Therefore, the size of, the norm of this ideal, which is the size of OK, my alpha is just the product of the sizes of all of these things, which is just the product over I of the size of these mi's. Great. So I should be careful and make sure I write enough brackets. So this is the norm of the ideal generated by alpha. So yeah, if I take norms here, that's the norm here. So the size of this group is just the size of this group times the size of the next one, and so on. And each of these groups has size of mi. Cool. So now we need to relate this number to the norm of the normal norm. So now let's relate this to the norm from K to Q of alpha. So let's look at all these bases that we've written down, and we're going to compare this. So, as I said, for this, we compare think of these, that we have 3 bases. So I gave you 2 bases for alpha, but I have 3 bases for k over q, which are, I gave you the first one was just the E1s up to En. If it's a basis for the ring of integers, then it also works as a basis for the full field. Similarly, I have M1, E1, Mn, En. Again, I've just multiplied with my basis elements by some integer, so this is still a basis for the full vector space. And lastly, I have this other one, alpha times E1, alpha times En, which again I've just taken my basis and multiplied it by some random element. This is still a basis for my full vector space. So let's try to understand this change of bases matrix that we have here. So we have the following diagram. Comparing the change of bases matrices. So let me just write this out. So I have these are change of bases between the vector space K. So I have the map K to K given by, I change my basis from EI to this alpha to the EI. This is that change of basis. I have one here from K to K, which is just does nothing. EI gets sent to EI. Now let's do this one. I have EI changes to MI times EI. This is my other change of basis. Okay, and then I have the map between these two things, which is the MI EIs gets sent to alpha times EI. So I have this diagram of 4 maps representing these change of bases. Here I'm changing from the EI basis to the alpha EI basis, and from the EI to the MI alpha basis, and then so on. And you'll see that doing these things together is this diagram commutes. So here I've done nothing. Here I've changed to the MIs, and here from the MIs I've changed to the alphas. It's the same thing as just starting with the EI, then changing to the alphas. But remember this, just because this is just like the map given by multiplication by alpha. So at the top row of this corresponds to the action of the standard representation of alpha, which we call A alpha. So I'm going to write A alpha here. This matrix is just the identity matrix. So the left arrow is identity. Matrix, which I'm denoted by I. This one along the bottom, this is some matrix which is diagonal, and it has MI entries MI along the diagonal. So bottom arrow corresponds to D, the following matrix. You just have M1, Mn, and zeros outside of it. I take my basis M1, E1 to M1 times E1, and so on. And this matrix here, this is the change of basis matrix between these two different bases. And the key thing to note is that this is a change of basis matrix between two different integral bases. We said that these two things were integral bases. So whatever this matrix is, we know that it's going to have integral entries, and determinant is going to be plus or minus 1. So if I denote this matrix by n, so the right arrow, I'll keep this in the right. The right arrow corresponds to a change of basis matrix n between two integral bases Therefore, we've seen this before. Therefore, we know that the determinant of n has to be plus or minus 1. And I guess obviously n has integer coefficients or integer entries. So because this diagram commutes, it's telling me that this matrix is the same thing as doing this matrix and this matrix and this matrix. So since this diagram commutes, we have, so make sure you get the order right, but this is n d I, because we do I first and then d and then n. So we do I first and d then n, and so this is the way it comes up. So as matrices, this is what they look like. But now the first definition of norm that I gave you, which was the determinant of a alpha, was the norm of alpha was the determinant of the standard representation of alpha, a alpha. So therefore, we have the following. We have the norm k to q of alpha, which is the same thing as the determinant of alpha, which is the same thing as the determinant of n times the determinant of d times the determinant of the identity matrix. What is this equal? This is, well, the determinant of n is plus or minus 1, so this is plus or minus the determinant of d. The determinant of the identity matrix is 1. But remember that d, we know what the matrix D is. It's this diagonal matrix with mi's along the diagonal. So this is plus or minus the product over I of these mi's. So coming back up to the first thing we proved, we'd proven that the norm of this ideal was the same thing as the product of these mi's up to the absolute values. So if I just take absolute values of this, I get the result. So maybe this is a typo in the theorem. Maybe I should have put, yeah, I'm missing a plus or minus. Therefore, the norm k to q of alpha, this thing equals I of mi, which by the things we saw above was the same thing as the norm of this ideal alpha. Great, so I should just go back and fix the absolute value of this norm is the same thing as this thing. So the absolute value is because I need to get rid of the plus or minus 1. Great. So this is why, maybe the best reason why the norm of an ideal is called the norm. This thing. It's because when you take the ideal generated by a single element, it coincides with the norm of the element up to sign. So let me do an example. It's time for an example. So, let me take out mod prime. P B mod prime and zeta p p through to unity. And as we saw before, that this lambda p is going to be 1 minus zeta p. I'm going to let k be my usual cyclotomic field, so k is zeta p. Then from the proof, if you remember the proof of this theorem where we were calculating the ring of integers for these fields, the proof of theorem, I think this is what this theorem was, 2.3.2. We know that, so in that theorem we checked that the norm of this element, lambda p, was exactly p. Therefore, using this theorem, the norm of the ideal that this element generates, which is notice that this element lives in OK, so it makes sense for me to talk about this ideal. This is the same thing as the norm, well, the absolute value of the norm from k to q lambda p, which equals p. And then by the result that we saw above, it told us that if your norm the norm of your ideal was prime, then your thing will have to be a prime ideal. So by the above, no, what was it? Let me just get the number. 3.4.4. We have that this ideal is prime. Great, so we could calculate the norm of this ideal. I mean, now it tells us it was prime. And before I finish, let me just give you some short results or corollaries from this result that I've just proven. So here's the first one. So corollary 3.4.7, which says if I have a number field and A and OK an ideal, I should say a non-zero ideal. And I pick some element inside of it, alpha is some element A, then this ideal is principal, so it's generated by alpha, if and only if the norm, absolute value of the norm of this element equals the norm of my ideal. So this is almost immediate from what we've proven. So yeah, since alpha is in A, we have that the ideal generated is also in A. So we have this is contained in the ideal generated by alpha is in A. Then by this lemma 3.4.3, which told us that if you have containment of ideals and then things have the same norm, then they have to be the same. So using this and prop 3.4.5, we get the result. So this lemma 3.4.3 told us that if you had one ideal containing the other, but they both have the same norm and they were the same thing, and this proposition tells us that the norm of the ideal generated by alpha is the same thing as the norm of alpha, which by assumption is the same thing as the norm of A. Great, so that's the first one. Now we have a short lemma. I'm not sure why I call this a lemma, but 3.4.8. If I let K be a number field, and I have some ideal in OK, a non-zero ideal. Stop saying non-zero. That we should always just think of proper ideals anyway. And I'm going to let A be the norm of this ideal. Then A is contained in my ideal. So the ideal always contains its norm. So proof. This is going really back to basic group theory. Recall that by Lagrange, Lagrange's theorem, every element of this integral domain, this is some finite integral, so this is some finite ring. This has order, every element of this has order dividing the size of the, so if I have, think of this as an abelian group. If I have an abelian group of size NA, then every element in it has order dividing the size of my group. Well, actually, and I guess it has order at most NA. Therefore, if you look at the element one plus my ideal in this quotient, so just the number one in this quotient, we have, if I multiply A times, this has to be 0 plus a, because my little a is a norm. So this is the size of my group. So if I take my identity, well, this isn't the identity element, this is an additive group. But I take this element and I add it to itself a times, then by Lagrange, this has to be 0. It has to be the order of the group, which implies that little a is in my ideal a, right? I have 1 times this, write this out. This means that a is inside this ideal. Great. This is actually quite useful, this little lemma. This is why I call it a little lemma, a lemma, not a corollary. Yeah, we saw something like this in the proof of proposition 3.2.4, where we were trying to prove that these quotients were always finite. We found some integer inside of our ideal and used this to check this is finite. And I'm somehow telling you that this integer can be taken to be this norm of this element. And the last thing, so corollary 3.4.10, which is let K be a number field. Then there exists only finitely many ideals of a given norm. So there will only ever be, some finite number of ideals of norm 2 or 4 or 5, whatever. This is going to be used heavily when we try to study this group of ideals that we've constructed. The fact that there are only finitely many of any size is really useful. So let's prove this. So if A is an ideal with, let's say, norm of A, I'm calling the norm of A. These are 2 different A's, but I'm sorry for the notation. It's just that Fraktur or Gothic A's are very standard notation for ideals. So if I have an ideal of A with norm A, then by this lemma 3.4.8, the one that we just looked at, we have A has to be contained in my ideal. Just check this, which means that, well, it means that the ideal generated by A is contained in A, which implies that A divides this ideal, because containment turns into division. But by uniqueness of factorization into prime ideals, to prime, not into prime ideals, this is just standard uniqueness of factorization. A has only finitely many factors, which you can see gives the result. Great. So this is where we're gonna stop for now. So we now have norms of ideals. We will do lots of exercises for computing the norms of ideals, but the first thing, before we get there, let's just construct the ideals that we want to take norms of. So we're going to look at taking like a prime number, and from this constructing ideals in our number fields which are interesting, well, in our rings of integers which are interesting, and then we'll figure out how to tell what the norms of these things are. But I'll leave it here for now.